Okay, so we already alluded to this before at the very beginning of this. PowerPoint, we were talking about those factors that affect the rate of reaction, meaning it makes it go faster or slows it down, and such, right? And so, of course, temperature, right, will affect the rate of reaction. And the reason why it does is because it increases the frequency of the collisions of the molecules, right? And the more times those molecules collide with each other, the more likely they'll react with each other, right? And then, of course, the orientation of the molecules. It turns out that these molecules have to be in the perfect orientation for them to be able to have their p orbitals overlap, right, to make a new compound, right? So they also have to be in the correct orientation. So if there's more collisions, there's a higher chance that the orientation of the molecules are going to be correct, right, to proceed with a reaction. And so the thing that we're going to be talking about today, right, is called the activation energy. It's the energy needed for a reaction to take place. It's called the activation energy. Okay, that's our important topic for today, activation energy, right? Activation energy. Remember that phrase, okay? Remember that phrase. So let me see here. I didn't even log into my thing yet. So talking about temperature, right? Talking about temperature, uh, generally as temperature increases, the rate increases, which makes sense, right? Uh, because I just said if you increase the temperature, you increase the frequency of those collisions between the molecules, and the more you increase the frequency of collisions, the more likely that the molecules will collide with each other, and then also more likely that the molecules will collide each other in the correct orientation to cause a reaction to occur, right? And so what you're seeing there on the right hand side is actually a picture of a glow stick, one in hot water, one in cold water, right? And glow sticks, when you break them, there's two chemicals that mix together and they fluoresce very, very brightly, right? They fluoresce really brightly, or glow, if you want. That's why they're called glow sticks. Um, but when it's in cold temperature or cold water, right, the glow isn't as bright. But when it's in hot water, the temperature is much, much brighter. And so that's just an example of how heating something up will increase the reaction. And this happens a lot, especially in organic chemistry. I was telling you a little while back how when you do an organic reaction, you can use this thing called a reflux. And in a reflux, quite literally, what happens is that it was that story I told you where I had the reflux going overnight and the hose popped off and then the water went everywhere and it flooded the third floor. Yeah, maybe I told that to a different class. I don't know, but that was a pretty bad situation anyway. Um, but anyway, so in a reflux reaction, you have your reaction mixture, and it's like bubbling, right? You have your reaction mixture, and it's bubbling, and what happens is that the reaction mixture will start to evaporate. But then we have this thing on top of it called a condenser, and it keeps all the vapor inside, so that you can keep on doing the reaction. Keep on doing the reaction while it's still hot. Sorry, I got to put in my freaking code here for getting into Wesleyan again. It's like they don't know I work here. 379376. There we go. Yes, stay signed in. It never works, but stay signed in anyway. Um, and it also says here, do not reveal this code to anyone. So I guess I should have kept my mouth shut when I did that. Anyway, so the rate is constant. Sorry, the rate constant is temperature dependent. It increases as temperature increases. The rate constant doubles with approximately every 10 degrees Celsius rise. Right. So here's a reaction where we have I forgot what it was called, but I remember that's acetonitrile. So whatever it is that becomes acetonitrile, right? the As the temperature increases, you can see how fast the rate rises, right? How fast it rises. So the hotter it gets, the better it is for a reaction. Okay, the hotter it is, the better it gets for a reaction. So let's talk more closely about the frequency of reactions, or sorry, the frequency of collisions, right? So there's this thing called collision theory, right, or collision model, and that states that uh, molecules must collide to react, right? It's based on the kinetic molecular theory. If you guys remember, the kinetic molecular theory was the kinetic molecular theory of gases. Remember that? And in the kinetic molecular theory of gases, it said that molecules of gas are very far apart, and they bounce around inside their container in random but straight directions, right, until they collide with each other, and that's what causes pressure. Do you remember that, the kinetic gas theory? You can always look that up later. It's not as important as doing the collision model, right? Molecules must collide to react. If there are more collisions, more reactions can occur. So if there are more molecules, the reaction rate is even faster, right? So that's just based on the the zeroth order, first order, and second order type of reactions, right? Because if there are more molecules, the reaction is faster, right? So that's like a second order reaction where if you double the amount of molecules, you get the double the rate, right? And it gets even faster if you heat it up. In a chemical reaction, bonds are broken, and new ones are formed. So molecules can only react if they collide with each other. So that's like 5 different ways now I've said they have to collide with each other, right, to react. Okay, so wrong computer. So the orientation of molecules. Okay, molecules can often collide without forming products. Aligning molecules properly can lead to a chemical reaction. The bonds must be broken and made, and the atoms need to be in proper positions. So here, excuse me, here we have green is usually chlorine, all right? And so here's a chlorine molecule about to collide with another molecule that may have a chlorine there too, right? And if it's going to hit the chlorine model end on end, we already know chlorine likes to be with itself, right? Because it's one of those diatomics. Remember that? So chlorine already likes to be with itself, okay? And so this chlorine atom collides with this chlorine atom right here that's attached to this. So reaction occurs. A new bond forms to make the chlorine diatomic molecule, right? Chlorine gas, and then the rest of this stuff flies away, right? But the problem is that if you had a collision where the chlorine molecule, is not faced so that the chlorine atom collides with it, then this chlorine atom will just collide with, let's say, usually red is oxygen, right? So it collides with this oxygen, right? And it just bounces off, and there's no reaction at all, right? So the more collisions there are, the more likely that you have the orientation, the molecules in the right orientation. So you get a chemical reaction where uh, chlorine gas is released, right? And then you have this leftover product right here. But you also have some that, it collides incorrectly, you have no reaction happen at all. Okay, so both of those are super, super important um, for a reaction to occur. So, your first question for today is this: which of the following does not happen during a chemical reaction? Molecules avoid each other, bonds are broken, new bonds are formed, or all these happen during a chemical reaction? Let's see here. So far, I only got 2 responses, 3 responses. 4 responses. 6 responses. How many people are here today? 10? Yes, 10. So we need 4 more people to respond. Read this question carefully here, okay? Which of the following does not happen during chemical reaction? Molecules avoid each other, bonds are broken, new bonds are formed. Got 7. We're waiting for 3 more people. 8, 9. One more person. 10. Okay, good job. Good job. All right, so the vast majority of you picked A, which is correct, right? Uh, it's definitely not C. Well, it can be C because C is one of the things that does happen in the chemical reaction, but it can definitely not be D, right? Because you look at this answer right here, if you look at these questions and this answer, right? Bonds are broken, so that's correct. B is correct. New bonds are formed, that is also correct, right? But what did I just harp on for like 5 minutes just a second ago? Yes, molecules must collide for a reaction to occur, right? Molecules must collide for a reaction to occur, but that says molecules avoid each other, right? So make sure you're reading these things carefully and you're listening to what I'm saying, right? Especially those people who picked all of the above, okay? I'm not saying these things 5, 6 times so that, for my health, all right? So make sure you're listening and you are reading the question carefully, okay? All right, so continuing on. The minimum energy needed for a reaction to take place is called the activation energy, right? An energy barrier must be overcome for a reaction to take place, much like a ball must be hit to overcome the barrier in the figure below. So here we are, a golfer is playing some golf, you know, and he's going to follow. Well, I guess he's not following through because he's just putting right now, but he's got to go over this hump here, right? And this hump here is like an activation energy, the energy required to make a reaction happen. The problem with this picture, though, is that it's not very accurate, right? It's not very accurate because the land over here, the level of the land over here, and the level of the land over here is the same, right? Generally, what happens in an activation energy is that, and the reason why reactions occur to begin with, is because you have a molecule and it's already at this certain energy, right? It wants to turn into something else, so it goes over the activation energy, right? But the reason why it wants to do that is because going over the activation energy to become this new molecule is lower in energy than being the way it was originally, okay? So there's got to be some kind of energy benefit during this reaction, right? There's got to be some kind of energy benefit. And many times, right, molecules become other molecules because the product is less energy, right? It's more stable. And this is quite true with our example with salt, right? With sodium and chloride. Remember that chlorine gas by itself can kill people, very, very deadly. And then sodium metal is also very explosive, right? But we put them together, and none of those things are true anymore about those two combination, right? Now they're on top of your popcorn, right? Or I used it to season my steak yesterday, right? So the salt molecule, sodium chloride, is far less energy, far more stable than both the chlorine atom or chlorine molecule, gas molecule, and the sodium molecule or sodium metal, right? If they were separate. Does that make sense? Right? That's what activation energy is. So there's this thing called the transition state. Okay, there's this thing called the transition state, and it's exactly what it sounds like. Where are you going? Oh, okay. I got so sad. I was like, I thought this was a riveting lecture. Anyway, so transition state. So, and when you're talking about transition state, the transition state is that part of the activation energy at the very top when the molecule is changing to the new molecule, right? So it's quite literally what it sounds like. It's transitioning. It's the state in which the molecule is transitioning, right? Reactants gain energy as the reaction proceeds until particles reach the maximum energy state. The organization of the atoms at the highest energy state is called the transition state, or the activated complex. The energy needed to form this state is called the activation energy, right? So just remember that the transition state is the state in which the molecule is becoming the new molecule in the reaction, okay? So here's what it all looks like when we take it off of the golf course, right, and actually use some chemistry graph, right? Because we use a lot of graphs in chemistry, I know, right? So here is a plot called the reaction progress plot. Okay? On the left-hand side, on the y-axis, we have a potential energy. on the x-axis, we have the reaction progress. That means how much time is passing by, right, as the reaction is proceeding, okay? And so here we have that molecule that I can't remember what its original name is, right? Isonitrile something or other, I can't remember. Methyl isonitrile, who knows? But it's becoming acetonitrile over here, okay? And notice what I said before, right? Remember we had the golf course where the thing was flat on both sides of the hill, but in real life, an activation energy usually has its product lower in energy. See, you see how the acetonitrile right here is lower in energy than its original reactant, right? So, I mean, what's the point of a molecule becoming another molecule if it's not beneficial to it, right? And for most molecules, just like most people, stability is what they want, right? A stable relationship, stable emotions, stable finances, right? That kind of stable job. Molecules just want stable energy, right? They want stable energy. And so there's no reason for a molecule to go through this heat activated activation energy thing, go through all this trouble right here just to become acetonitrile if it wasn't going to be beneficial to it, right? So we start here. This is the reactant, right? And the reaction begins, and then this part right here, the energy between the products, the reactant's energy and the energy required to get to the activated complex, or also known as the transition state, right? It's called the activation energy, right? So this is the energy between the reactant and the energy needed to get to the transition state. That's called the activation energy right there. And you always know you always know that there's a transition state, for one thing, because it's always at a peak of one of these things. But then also when you look at the molecule up there, you see how the CN right here, the cyano group, or the also known as the cyanide group, right, is starting to bend, right, as it goes up this hill, and then it starts to rotate. And when it's rotating, you see that there's no bond there anymore. What do you see there? You see three dots, right? Those three dots means that it's going through transition, it's changing, right? It's going through transition and changing, flipping around, and as soon as it flips around, right, and becomes the acetonitrile, it's so much more happy, and it's a downhill turn now, right? It's just going downhill to become acetonitrile, which is way less energy than the original reactant. So the other thing you need to know from this plot is that the energy between the reactant and the product, which is this orange one right here, is the change in energy, right? And there better be a change in energy that's beneficial to that product, right? Or it's not going to happen. This reaction won't happen, right? Imagine if, for example, if acetonitrile wasn't way down here, but its product was up here, right, in energy, would that reaction proceed? No, because now the product is more energy than the reactant is, right? So since it's lower in energy here, it wants to go down there. It wants to go through and get more stable, switch things around. It's kind of like getting a new job, right? So it's this molecule's original job was just so unstable. It didn't have any like. Oh, that's actually a good example would be me. So when I was a forensic scientist, I was actually doing adjuncting, like part-time teaching at the same time, right? But that wasn't very stable. Like it was based on semester per semester. If the school needed me to teach, right, then I would teach. But if they didn't need me to teach, then I wouldn't teach, and I wouldn't have a teaching position that semester. So that was a very unstable position, right? But then Wesley called up and was like, "Hey, we'll give you a full-time position where you can teach all the time. No worries about not having a class to teach one semester or not, right? That's a more stable job." So I left the adjunct job, the part-time teaching job, right, and came here because it's a more stable job, right? It's the same thing with molecules. They're leaving a worse situation over here and becoming a quite better situation here, right, on the other side. There's no reason to go through all that work, right? If you're not going to be in a better situation. What happened? Which one right here? This line right here, the dotted line. Oh, you got the red line. Which one? Yeah, that's what I'm talking about. This energy is lower than this energy. That's why this molecule wants to become acetonitrile, right? right? If a job, as an analogy doesn't work, think about it being like maybe a volatile relationship, right? And you're like, man, this relationship was super fun at the beginning, right? Because it's so crazy, right? And then you're like, okay, I need to get a new girlfriend or something because I don't know, I need more stability in my life. I'm a homebody, and so you break up with your girlfriend, and then actually it's probably the opposite. My girlfriend would do that to me. So anyway, because I used to be super crazy. Anyway, she'd break up with me, and then she'd find a more stable boyfriend, right? And that'd be her now. Less energy, right? They wouldn't have as much fun, right? My girlfriend and her new boyfriend, but at least it's not as crazy in their relationship. Okay, your next question. Which of the following is true about the reaction process? At the lowest energy state, the transition state is formed. The reaction can only be exothermic after the transition state. The rate constant depends on the magnitude of the activation energy, right? Or none of these statements are true. Okay, which question was this one on the Microsoft forums? Since I wrote these so long ago, there's like a whole bunch of other classes in between, so I have to find it. Ah, reaction progress. I bet you that's it. There it goes. Got 4 more people. I didn't outrightly state this yet, so I'm seeing you guys can make some connections here between the last few lectures and this. 2 more people? 1 more person? Still waiting for that 1 person? There we go. Wow, there was an answer for every one of them. That's crazy. But that's okay. I didn't outrightly say this, so I just wanted to see how this was going to go. The vast majority of you picked C, which is correct, right? C is correct. We know already, right, that, let me switch back to the laptop. We know already that the highest energy state is actually where the transition is, okay? We also know, so that's incorrect. We also know that a reaction doesn't have to be exothermic all the time, right? It can also be what? Endothermic. So that's incorrect. But this one right here, rate constant depends on the magnitude of the activation energy. That makes sense, right? If the activation energy is lower, then the rate constant doesn't need to be as high, right? The speed can be faster. Does that make sense? Right? I did not rightly say that, but I was hoping you would make that connection, which most of you did. I'm very proud. Good job. Okay, so, whew, starting to run out of energy already. Where's my activation energy at? Um, Distribution of energy of molecules. So the 2 things that you need to know from this slide, or these 2 lines right here, gases have an average temperature, but each individual molecule has its own energy, right? At higher energies, more molecules possess the energy needed for a reaction to occur, right? So uh, this is the thing I was telling you about before, where you have like a puddle of water on the ground, right? And it's just regular room temperature. If you just leave that water on the ground, eventually it would all dry up, right? Because some of those molecules have the energy, enough energy for it to evaporate, but most of them don't, right? So it just takes some time, a lot of time, right? But if you heated up the water, right? If you had like a heated floor, right, and you heated up that puddle, what would happen? The water would evaporate faster, correct? It's the same thing here, right? Same thing here. Most gases have just average temperature at room temperature, right? But some of them do have enough to actually do a reaction, right? But if you want more of them to have enough energy to do the reaction, you just heat it up, give it more energy. And we're using energy and heat synonymously here, okay? Like heating things up is the same thing in this case as increasing the energy, okay? So this is the one equation you need to know from this set of slides, okay? And I'm not going to try to derive it for you or anything like that. Don't worry. I know that was a little bit rough last time we did that, but Arrhenius. So funny thing about Arrhenius, right? Arrhenius didn't just come up with an acid-base theory, but he also came up with this equation here, right? Um, Arrhenius noted the relationship between the activation energy and temperature, right? And so notice right here we have the ideal gas constant and temperature right here, right? And we have the K here. You can solve for the activation energy, right? The activation energy also can be determined graphically by reorganizing the equation like this, right? Where we have this looks just like a y equals mx plus b equation, right? This is y equals mx plus b. So you can actually graph it too, the same way we did with the second order, the zeroth, first, and second order reactions, right? And then you can also rearrange the equation again, right? If you have both rate constants and you have the temperature you began at and the temperature you ended at, right? Then you can also solve for activation energy there too. So this is the only equation you need to know for this part of the thing. So when you graph, right? When you graph using that linear line, the line I just showed you, the y equals mx plus b equation I just showed you for activation energy, right? Where we have 1 over the temperature, right, on the x-axis, and then we have ln of the rate constant on the y-axis. The slope, right, is equal to the negative activation energy over the ideal gas constant, right? Which is great because all you have to do now is solve for EA. All you have to do is solve for EA, and you have the activation energy, right? So really, what this is even saying here is that the change in Y is the activation energy. Does it make sense? Right? Because the slope is what? Rise over run, right? And EA is equal to negative EA is equal to what? The rise or the change in Y, right? And so the activation energy is literally just the top number of a slope. Okay? Good stuff. Good stuff. So law versus theory, okay? Law versus theory. And this is in reference not to science in general, but in reference to kinetics, okay? Kinetics gives us what happens. We call that the rate law, right? For example, what happens when you add in twice as much concentration of reactant? The reaction rate doubles, right? Whereas, uh, whereas theory is different, right? Why do we observe the rate law? We use it to explain a theory, and the way we do that is called the mechanism. And I was telling you that before, where in organic chemistry, you'll have to go through and do some very detailed mechanisms on how bonds break and how bonds form, where electrons go, and all this stuff, right? To do a mechanism, right? But using the rate law, you can figure out some of the different mechanisms, right? A mechanism is a series of stepwise reactions that show how reactants become products. We won't be doing any of that here, right? But just be prepared for that kind of thing. Okay? Reactions may occur all at once or through several discrete steps, right? And each of these processes is known as an elementary reaction or elementary process, okay? Elementary reaction or elementary process, okay? All right, so this is your next question. Kinetics gives us what happens, which we call the description of the what? Okay, so let's see here. Forms, rate reactions, rate constant, no, not rate constant. Rate, here it is. Here it is. Got 5 answers so far. Nine answers so far. Just one more person. Un persona? Yes, there we go. One person. Okay. All right. So again, most of you got that one right. I am very appreciative. The answer is in fact B, right? I just said right before the question, the rate law tells you what happens, right? The rate law tells you what happens. And the question was in kinetics, what happens, which is kinetics gives us what happens, which is called the what? It's called the rate law, right? It's not the theory, it's not the mechanism, but it's the rate law, okay? So that might be a definition that you see on a multiple choice question on an exam, right? All right, so there's this other thing called molecularity, right? Molecularity. And so it's actually you get this in organic chemistry too, but it's pretty self-explanatory. So molecularity is just like applying a word to the number of molecules involved in the reaction, right? So, for example, here is we have unimolecular reaction is just one reactant, right? Uni meaning one reactant. Bimolecular reactions, right? Both of these are bimolecular because you have A plus A makes something, right? So that's two molecules, or A plus B makes, is two molecules. So that's why it's bimolecular, like bicycle, two things. And so an A plus A would be like two chlorines getting together, you know? Whereas an A plus B would be like a chlorine and a sodium getting together, right? Both of those still involve two different molecules, right? Or two different reactants, rather, okay? Termolecular, right? That comes from the Greek tertiary, which means three, right? And so three here, so this is three of them getting together. So this is like making an ozone, right? Three different oxygen atoms getting together to make ozone, O3, right? So that's three different reactants. Here we have two of the same reactants plus a different reactant, right? That's also termolecular. And then we have here termolecular is three different reactants. So the thing that I want you to notice about this, though, is that there is a rate law associated with each one of these, right? So, for example, one in a unimolecular reactant, right? Unimolecular, unimolecular reaction, not reactant, but reactant, right? The rate is equal to A, just A by itself, right? So that's a first order reaction right there, okay? Which makes sense, right? You double A, you get the reaction rate doubles, right? Bimolecular reactions, right? The rate is second order, right? Which means it quadruples every time you double the rate, the reactants, which makes sense because you have double the reactants in there already, right? They're the same reactant, okay? The other bimolecular is A plus B. So here, it's going to be the rate constant plus the rate constant of A plus the rate constant of B, right? Overall, this is overall this is a second order reaction, but on its own, they're first order reactions, okay? Here, this is the first time you've seen this before. This is a third order reaction, right? It's a third order reaction right there, okay? So A plus A gives you the rate equals the constant times the concentration of A to the third, right? And then here, A plus B gives you an overall, right? An overall third rate equation, right? I don't know what, I think that's a typo. There shouldn't be a plus sign there. So in your notes, you should cross out that plus sign between the on the bimolecular, because if you put a plus sign in there, when I ask you a question, it's going to be wrong. So get rid of that plus sign. That's a typo. Yeah, there shouldn't be a plus sign there. I'm surprised Mary didn't catch it. What's that plus? What's that plus sign for? Anyway, back to the termoleculars, right? The termoleculars, right, all have uh, uh, third order reactions, right? Because there's three reactants, number one. But notice also here for the termolecular that has the two of the same and one different, overall it's a third order reaction. And then here, A plus B plus C is also a third order reaction overall, right? Them individually, with respect to each other individually, they're first order, right? But altogether, they're overall they're third order reactions. So you could say then that the unimolecular tells you what the overall reaction rate is, right? The overall reaction rate for unimolecular is what? 1, or first. The overall for bimoleculars is 2, right? Or second order. And the overall reaction order for termoleculars are what? Third order. Make sense? Right? The molecularity of an elementary reaction tells us how many molecules are involved in that step of the reaction mechanism, which is what I've been saying the whole time. So let's talk a little bit about the termoleculars, right? Termolecular steps require 3 molecules to simultaneously collide. I feel like my tongue is colliding. Simultaneously collide with the proper orientation for proper energy. These are rare. If they indeed do occur, these must be slower than unimolecular or bimolecular steps. Nearly all reaction mechanisms use only unimolecular or biomolecular reactions, not biomolecular, bimolecular, right? And that's why when we went through kinetics the last couple of days, we only did like, 0th order, first order, and second order, right? Because you very rarely get the third order reactions, right? Okay, you very rarely, so let me rephrase that. You very rarely get the termolecular reactions, okay? All right, so let's talk about the limits of the rate. What limits the rate, right? The overall reaction cannot occur faster than the slowest part of the reaction mechanism, right? So it's basically like a bottleneck, right? In the reaction mechanism, there will be a step that's a bottleneck, right? And we call that the rate limiting step, okay? Because the rate can't get any faster than that bottleneck, okay? That's called the rate limiting step, right? So here in this picture right here, which I haven't actually seen yet, so let me study it real quick, right? So cars are slowed down at toll plaza A, right? And so that's the rate determining step, right? In the passage through through A, because since they're being bottlenecked right there, slowed down right there, right? They're going to be slow getting into toll plaza B, right? Whereas if the cars are slowed at toll plaza B, the rate determining step is going to be at toll plaza B, right? So it really is like a bottleneck. You can't go any faster than the reaction if there's a step that slows everything down. Okay. So what then is required? What then is required of a plausible mechanism, right? What do we need to have a plausible mechanism for reaction? Well, the first thing is that the rate law must be able to be devised from the rate determining step, right? So what that means is that your rate law will not be based on any of the faster steps of the reaction. It's always going to be it's going to always be based on the rate limiting step, the slowest step of the reaction. Okay. The stoichiometry must be obtained when all steps are added up. All right. And then, of course, the stoichiometry is the coefficients of the reaction, right? They all got to balance. Each step must balance. I just said that. Each step must balance, just like any other equation, right? And the intermediates are made up and used up, right? So whenever you have a reactant, right? For example, you have 2 chlorine atoms as reactants. They do their reaction to each other, right? And they become chlorine gas on the other side of the activation energy, right? There's no more chlorine left over. Everything has to be used up. Does that make sense? Right? Okay, so that's an important step there. Contrast this with this here, which is a catalyst. A catalyst can be used to increase the rate of reaction, lower the activation energy, right? But once you're done with the catalyst, like nothing else matters anymore, because the catalyst is just, you can just take it out and it'll be the same, right? So the important thing about a catalyst is that a catalyst can be used in a reaction, but it's not a part of the reaction equation, right? Not a part of the reaction equation. Okay, catalyst. All right, catalyst. This is more important. This is what I think is more important. Catalysts increase the rate of reaction by decreasing the activation energy of the reaction, which I said that before, right? Catalysts change the mechanism by the process by which it occurs. So here's our reaction diagram again, our reaction energy diagram again, and our normal reaction with hydrogen peroxide here, right? Becoming water and oxygen, right? It's got this super high activation energy. But again, this is an exothermic process. So when it gets down here, it's actually lower energy because obviously water and oxygen are lower energy than hydrogen peroxide. But when you have an enzyme in there, right, or an enzyme or a catalyst or something in there, it can actually make the reaction go much faster, right, because it lowers the activation energy. Okay, it lowers the activation energy. So um, I think if you look right here, you can see that there's a Br right there, right, a bromine right there, and the bromine doesn't really do anything but act as a catalyst because you get two bromines there, two Br minuses there, right, and you get two Br minuses out, right, but then the reactants change, right? You had two hydrogen peroxides and you had some protons, but uh, now you have two waters and two oxygens, right? So the Br and the two proteins are the catalyst, right? And the H2O2, the hydrogen peroxide, is the reactant, and the products are water uh, and O2. So oxygen. So what I want you to be able to do from a reaction diagram like this is to look and see which is the products, right? Which is the product. Here it's hydrogen peroxide. Which is the reactants? Here it's hydrogen peroxide. Which are the products? Water and oxygen. And then which is the catalyst, right? And the catalyst here, the thing that doesn't change, but is there to help the reaction go a little faster, is the Br and the hydrogen, right? So be able to look at these reaction diagrams and tell the difference between a catalyst, a product, and a reactant. All right, so there are three types of catalysts. There's a homogeneous catalyst, there's a heterogeneous catalyst, and there's an enzyme, right? Enzymes are biological catalysts. That's what I studied when I was in grad school. I studied a bunch of enzymes. There's a whole thing called enzymology, right? So in a homogeneous catalyst, the reactants and the catalyst are in the same phase. Many times, reactants and catalysts are dissolved in the same solvent, as seen below, right? So a homogeneous enzyme would be like both the catalysts are liquids, right? Or they're dissolved into the liquid, or something like that, where you can't even really see after you've added the catalyst that the catalyst is there. Okay, so that's a homogeneous catalyst. It makes sense because homogeneous means the same, right? And then this is the reaction I was talking about before, right? When I was talking about the hydrogenation of fats, okay? That's a heterogeneous catalyst because the catalyst here is this platinum metal, right? This platinum metal right here, okay? And then the reactants are actually going to be the hydrogen molecule there and the hydrocarbon, like a fat, right? And when you have this heterogeneous catalyst, the platinum stays platinum. It's still a metal, a solid, right? But the gas is still gas too. So they're not the same phase, right? In the homogeneous catalysts, they're same phase. But in the heterogeneous catalysts are not the same phase, right? We have a gas here, but we have a solid here, right? And so the catalyst will help the two molecules get closer to each other, and then the platinum will add the hydrogens to the molecule, right, making a new molecule. So that's the same thing I was talking about before with the double bonds in a vegetable oil, right? It'll add hydrogens to the double bonds of the vegetable oil, and the way it does it is by using a catalyst like that, right? So that's called a heterogeneous catalyst, okay? So the thing I need you to remember about that is heterogeneous catalysts are different phase, whereas homogeneous catalysts are normally the same phase. Okay. So you don't have to scan this. We'll just talk about it real quick. Which of the following is not true of a heterogeneous catalyst? The reactant and the catalyst are dissolved in the same phase. That's definitely the one that's not true. The catalyst is a different phase than the reactants. That's true. Absorption of the reactants is often the rate limiting step. That's also true. So A is the answer there, right? Because reactants and catalysts dissolved in the same phase is usually what? The homogeneous catalyst, right? It's usually the homogeneous catalyst. And then we're heading to the pretty much the end now here, right? Enzymes, which are my specialty, are biological catalysts, right? You wouldn't be alive if there weren't enzymes in your body because the vast majority of the reactions that happen in your body right now, like in metabolism, like the TCA cycle, glycolysis, the electron transport chain, amino acid stuff, the DNA replication, all those happen by enzymes, okay? And how it does it is that the enzyme will actually create this little microenvironment. What it's called the active site, right? And then the reactants go into this active site, and the enzyme like forces the reaction to occur. Okay. It forces the reaction to occur. So when you have reactants in an enzyme reaction, they're actually called substrates. That's important. So remember that. Reactants in a biological catalyst or an enzyme are called substrates. So you always have the enzyme and the substrate, right? And then, so the substrate is like the molecule, and the big enzyme comes over and grabs onto it like this. That's called the enzyme substrate catalyst, right? I mean, enzyme substrate complex. And that's what forces a reaction to happen that would normally not happen. So a really good example of this is beef liver. It's got this enzyme in it called catalase. You'll find that every enzyme ends in ase, right? Catalase. And catalase will actually, this inside beef liver, will turn hydrogen peroxide into water and oxygen, right? Which is actually the exact same reaction we saw previously here. Here, with the bromine, excuse me, with the bromide ions and the protons, right? Which is basically hydrogen bromide, right? Hydrogen bromide, or hydrobromic acid, or hydrogen bromide gas, right? It's the same thing as that, right? But we don't want to use acid. If you use an enzyme called catalase, it will do the same thing. It will do the same thing. It will turn the hydrogen peroxide into water and oxygen, right? And then the catalase can still be reused again, right? It can still be reused again. This is actually, if you go to biochemistry, like the next class, not the next class is organic. The class after that is biochemistry. I think you actually do a reaction with this because um, the biochemistry professor was actually looking for beef liver the other day. So I think they're actually doing it now. It's actually a lot of fun too. Good old catalase. And then this is the last slide here. So I was talking to you before about how we have substrates and enzymes. Enzymes are actually mother huge. They're really big things, right? They're very large molecules. They're made of proteins, and well, let me rephrase. Enzymes are proteins, and they're made of amino acids, which you'll learn about that later on in life, right? But they're huge molecules, and they have this little thing in there, this little spot in there, right, called the active site. And the active site, for, this is very simplistic, but it has a place that's perfectly suited for the substrate to enter, right? And when the substrate, remember the substrate are those reactants, right? The substrates are the reactants. When those substrates or the substrate enters the active site, the enzyme will conform it and move it around and change it so that the environment around it will make it so that the substrate is more likely to react and become something else. And that's called the enzyme substrate complex. So after it's done doing its reaction, the enzyme will let go of the products, right? These are the two products now, it just lets it go. And then all you're left with is the enzyme. And notice that the enzyme remains unchanged throughout this reaction, but the substrate changed to these two things as the product, right? So in the enzyme substrate model, the substrate fits into the active site of an enzyme, which is much like a key that fits into a lock, and they're very specific. So this is very simplistic in what it's saying because in real life, it's not exactly lock and key like this. In fact, the enzyme is a very dynamic molecule, and the substrate, when it gets close to the enzyme starts to fold around it. Like it will actually be dynamic and move around it and stuff like that. So it's not just as simple as lock and key. There's a lot of movement happening to actually make it happen. Okay. All right. So I do want you to answer this last question though. So scan this just to make sure, just so I know that you guys got done with all this right here. Which statement is true about enzymes? They are biological catalysts. They have a region called the active site. They are specific, or all these statements are true. All right. Well, see, it's a good thing that you're here to scan this now because then I can count you to be here today. Are you in? Is everybody signed, answered? I don't want to have to log into the computer, so that's why. I want to see who actually stayed for discussion after I said you have to stay here the whole time. compared to who is still in class, which most of you are here, so I'm very proud. I'm very happy about that. Everybody signed in? Yeah, good, right? All right. So what is the answer here? It's going to be D, right? They're all these statements are true. In fact, enzymes are biological catalysts, right? They have a region called the active site where the reactants attach. What are the reactants called when you're using an enzyme? Substrate, exactly. They're called the substrate, and they're super specific, right? And then all those statements are true.